Okay, this video is to take place of the actual lesson you would receive in class. And so this one is going to be on what we call natural logarithms. But before we get into what a natural logarithm is, we got to talk about its base. And so that's going to take us back to exponential functions, which is something you learned in Math 1 and Math 3, but I don't believe we worked with what we call the natural base. So you should have a copy of these notes. If you don't, ask the substitute for them and follow along with me in this video. So what we have here is, what is E? So E is an irrational number. So E is an irrational number, meaning that its decimal will never repeat itself, and it'll never stop. So it's an irrational number. And its approximate value is 2.71828. And then I believe it goes 1828 for a while, but then every once in a while you'll get another digit. Now, this base of E often occurs as the base of exponential and logarithmic functions that describe real-world scenarios. That's a lot of the times where it comes up. That's how it was discovered. So our purpose in studying is that we can solve real-world application problems that may involve the natural logarithm. So base E functions, let's take a look at that before we get into what our logarithmic functions look like. So exponential functions with a base of E are called natural base exponential functions. An example of a natural base exponential function would be something along the lines of y equals. I just have to have E as my base, and then I could raise it to the 5x power. And that would be an example of a natural base exponential function. It's exponential again because the variable is in the exponent. Ones that we've looked at previously, we've always had a whole number or an integer in the base. This time now we have an irrational number in the base. So where we really need to work from is what we call a logarithmic function with a base of E. So if I have a log function with a base of E, this is called a natural logarithm. Up above, we said it's a natural base exponential function. Here, what we're going to call it, though, is just it's a natural logarithm. And so this is any time I have a logarithmic function with a base of E. So for example, what it could look like, so I take my logarithm, have my base of E, and then I might have x minus 1. However, this is often abbreviated, and rarely do I ever see log base E such as this. Usually it's abbreviated as ln for natural logarithm, and then in parentheses I'll just put in the x minus 1. So in other words, what's happening here is that we're just replacing this log base E with a simpler notation, ln for natural logarithm. Now, this lesson actually had notes in it for converting between exponential form and logarithmic form. We're not going to worry about that because, again, we're going to be solving logarithmic equations, which certain forms of them are going to require us to rewrite them in exponential form. So we're skipping over that bit at the top. We're jumping right to number 4. And so, because those would have been the first 3. And so we're going to look at write each equation in exponential form. So anytime I see a natural logarithm, I know its base has to be e. All right, just like before when we looked at a logarithm, I'd look at the base of the logarithm, I'd write it for my exponential form. And then what the logarithm is equal to is the exponent, so here I'd have e raised to the 58th power. And then what I was taking the logarithm of is what the exponent will be equal to. So we have e raised to the 58th power is equal to x. In number 5, I have a natural logarithm. So I'm going to take e. This time the logarithm is equal to x, so my exponent now will be equal to x, or sorry, will be x. And this whole thing needs to be equal to 6. Then we have the natural logarithm of the quantity x minus 9 equals 32. Again, we have a natural logarithm, so that tells me my base is going to be e. It's equal to 32, so my exponent's going to be 32. And then we have x minus 9. So we've rewritten those 3 logarithmic equations in exponential form. All right, so the next part of this then is simplifying with properties. And so these might look a little bit familiar apart from we're not using logs with different bases, we're using natural logarithms here. Well, it turns out all of the properties of logarithms from the beginning of the unit still apply. So we still have the product property, we still have the quotient property, and we still have the power property. And they all still work the same way. So let's take a look at a couple of 3 examples to be exact. Because all of my properties, the product, the quotient, and the power property for logarithms still apply even if the base is e or we have a natural logarithm. So remember I stressed when we were doing these at the beginning of the unit, the bases have to be the same if I'm condensing. So since they're both natural logarithms, I know the base for both of them is e. It shows addition, so I'm going to use the product property, which says that if I have 2 logarithms of the same base with different arguments being added together, then I can condense that into a single logarithm by multiplying the arguments. So if I take 3 times 16, I will get the natural log of 48. In number 8, I still have 2 logarithms, same base, that both have a base of e, except in this one it's showing subtraction, and there's a 2 out here in front of this natural logarithm. Well, in our previous lessons, anytime I had a number out front, that was going to be part of my condensing. So what I'm going to have is I'm going to have natural log, the natural log of, and then because it's subtraction, it means I'm using my quotient rule, so I have 63 divided by 3 squared. Now, 3 squared is the same thing as 9, or it's equal to 9. So really this is the natural log of 63 divided by 9. And it turns out 63 is divisible by 9. And so our final answer here would be the natural log of 7. So we've condensed that down into a single logarithm, and it's just the natural log of 7. In number 9, we have a similar situation. I have a 1/3 in front of the natural log of 64, and I have a 2 in front of the natural log of x. We'll be doing the same thing. We're going to take those numbers and create them as exponents on the arguments using the power property. And then I see I have addition here, so I'm also going to use the product property. So we've got the natural log of 64 raised to the 1/3 power plus the natural log of x raised to the 2nd power. Now, my bases are the same on these logarithms, so I could go ahead and use the product property, but I'm going to simplify this right here first. Because 64 to the 1/3 power is actually 4. So this whole thing is going to simplify to the natural logarithm of 4 plus the natural logarithm of x squared. And again, because it's showing addition, I'm going to use the product property, which tells me what I need to do is multiply the arguments together. And it allows me to create a single logarithm out of 2 of them. So I have the natural logarithm of 4x squared. And then once we know what x is equal to, we can go ahead and evaluate it. But for right now, we were just condensing the logarithms. So let's talk about solving equations with natural logarithms. So all of the same processes, they still work. It's the same steps. So for instance, when I have a type 1, that's where I have log is equal to a log. I need to condense if I have to. And then I'll use the 1-to-1 property to essentially drop the logs. And then finally, that will result in a type of equation for me. I solve the equation and I check my solutions. So let's see what happens here in number 13. They both have the same base. They're both natural logarithms, so they both have a base of e. That's good. So step 1, it looks like there's no condensing to do. There's no isolating to do, so we're good there. So I'm going to go on to step 2. And that's where we just essentially drop the logs. We use that 1-to-1 property. So we have 4x minus 27 is equal to 15 minus 2x. So I'll come in and let's see. If I'm going to solve this, I'm going to add 2x to both sides. Add 2x to both sides. Move all the x's onto one side. This will give us 6x minus 27 is equal to 15. I got to finish solving. So let's see, I will go plus 27 to both sides. On the left, the negative 27 and positive 27 will cancel out. Then I'm going to be left with 42. So I have 6x is equal to 42. Now, finally, what I'm going to have to do is I need to divide by 6. Divide by 6. So 42 divided by 6 gives me a result of 7. However, what I have to remember is I've got to check for extraneous solutions at the end. So this is where I need to go back and make sure that it gives me equal values on both sides of the equation. So if I take 7 times 4, that is 28, minus 27 would give us 1. If I put 7 over here on the right-hand side, I have 2 times 7 is 14. 15 minus 14 is also 1. So the natural logarithm of 1 has to be equal to the natural logarithm of 1. So that means that this answer works. Now in 14, we have a little bit of condensing to do. All right, we have a little bit of condensing to do because we have this 2 up front. So when I go to solve this thing, that's what I have to take care of first, is any condensing or isolating. So I'm just going to go ahead and rewrite this problem. So I'm going to have the natural log of k. We're going to raise that to the 2nd power, and that's going to be the natural log of 2k plus 15. There we go. Now, I have a logarithm on each side. Bases are exactly the same, so I can go to that 1-to-1 property, and I can essentially drop the logarithms, and that just gives us k squared is equal to 2k plus 15. But now I need to take all of my terms and move them to the right because, to the left, because I have a quadratic equation. And to solve quadratic equations, most of our strategies require the equation to be equal to 0. So I'm going to go ahead and subtract everything from the right and move it to the left. So we've got a 2k, so we're going to say minus 2k. Minus 2k. And what that's going to give us is k squared minus 2k. And those will be eliminated, plus a positive 15. Now, I need to go ahead and take that 15 and move it to the other side, because again, I get to get this thing equal to 0. So we're going to have k squared minus 2k minus 15 is equal to 0. So I've got a quadratic, so now I need to think about solving. And the way I'm going to solve this is through factoring. So I need to try and think of two numbers that would multiply to be negative 15, but would add up to be negative 2. And that's right. It's going to be x minus 5 x minus 5, there we go, and x plus 3. And that will be equal to 0. So what we're saying here is negative 5 times positive 3 gives us the negative 15 as a constant, and it gives us negative 5 plus 3 would give me the negative 2 coefficient of the linear term. So now I'm going to use the zero product property, which just simply says if I'm multiplying two things together and their product is 0, then one of them has to be 0. So for the x minus 5, if I solve that for x, I'll get x is equal to positive 5. And if I solve the second one, x plus 3, I would get x is equal to negative 3. Now, I can tell you right offhand, because we always check these back in the original equation, looking at this first logarithm here, negative 3 is not going to work because I'd end up taking the natural log of negative 3. So I'm going to cross that one out. It's not a valid solution. Now I got to consider the 5. All right, so natural logs are a little harder to work with. But what I would look at in this case, if I were to put 5 in on the left, I'd have the natural logarithm of 5. I use the power property with the 2 to bring it up as an exponent on the 5. That gives us 25. If I plug it in on the right-hand side, I get 10 plus 15, which is also 25. So on both sides, we're taking the natural logarithm of 25. And since that works, that tells me that x equals 5 is a valid solution. All right, let's take a look at one more. We'll take a look at number 15, and then we'll go into type 2, where we have a logarithm equal to a number. All right, a logarithm equal to a number. So in number 15, there's a couple of spots of condensing that I need to take care of. First one's on the left-hand side. So I got a minus sign, so that tells me I need to use the quotient property, so that's what we'll do. We'll go in and use the quotient property. So I'm going to have the natural logarithm of 72 divided by 4. That's the logarithm when we condense it on the left. On the right, I've still got both natural logarithms, so I can work to condense those as well. Except over here, I have a plus sign, so this is going to be my product property. So instead of dividing the arguments, I'm going to multiply them. So we have natural log, and let's see, it's going to be 6a minus 12. Now that I have a single log equal to a single log, I'm going to use that one-to-one property and just ignore the logarithms. Because for them to be equal, their arguments have to be equal. So we're going to go ahead and just forget about the logarithms. And so I'm using that one-to-one property. And so I'm going to rewrite this as, let's see, we'll rewrite it as 72 over 4 is equal to 6a minus 12. That's just coming straight down. We're just taking the logarithms off of it because, again, the one-to-one property says for this natural logarithm to be true or equal to that one, then the two arguments have to be equal. My next step is going to be to come in and add 12 to both sides. So I'll come in and add 12 here. Those will cancel. I'll add 12 over here. And let's see what we come up with. Well, 12 could be rewritten as 48 over 4. So 72 plus 48. Let's see, that would take us up to 80. And I believe that's going to be 110. No, 120. Because that would be 48. So 8 would take me to 80. 40 would take me to 120. Right, we're going to have 120 over 4 is equal to 6a. And that's fine. If you can't do that, right, if you can't do that on your own, make sure you're going to Desmos here and typing in. Let's see, what did we have? We had 72 over 4. Plus 12. Now remember, Desmos is going to tell you, normally it would tell you a decimal if that's what it was, but in this case it's that whole number of 30. Okay, so this thing just simplifies down to 30 for me. So I could go ahead and do that. That simplifies to 30. So go to 6a. Then the last thing I have to do for solving is divide it by 6. So for this one, I'm going to end up with a is equal to 5. A is equal to 5. So let's go ahead and check that. So over here, we're just going to get, it would be 18. 72 divided by 4 is 18. And if I come over and put 5 in, that's 30 minus 12, which is also 18. So that tells me a equals 5 works. Or, like we had been doing with Desmos, we can do that as well. I could come back here to Desmos, and for a natural logarithm, you could just type in ln. All right, so we've got ln of 72 minus the natural log of 4, and I'll get a number for it. So there's my left-hand side. So now I'm going to come back and put in my right-hand side. So I have the natural log of 6 plus the natural log of a minus 2. And in this case, we think a is going to be 5. That's right. 5 minus 2. All right. And so we see that those numbers agree. So that tells us that 5 is the correct answer. Anything else would not have allowed the numbers to agree. All right. So that's checking with Desmos. All right, let's jump to a couple of the ones where it's like type 2 because we've got a log on one side and a number on the other. We've got a couple of them down here, 17 and 18, and that will be the end of the video. All right? It'll be time to practice your delta math. So in 17, I've got a logarithm equal to a number. So when that happens, remember, our steps were condense and isolate if necessary, rewrite it in exponential form, solve and check for extraneous solutions. So looking at this one, I can tell there's no condensing that needs to be done. It's already a single logarithm. It doesn't need to be isolated. It doesn't have anything being added, subtracted, or multiplied to it. So we're ready to convert this thing to exponential form. Now what we have to remember here is the base is going to be e. Our base is always e here. So we're going to have a base of e. And the exponent happens to be 2. Because remember, the exponent, or the logarithm, is equal to the exponent. And that needs to be equal to 8x. So switching between logarithmic form and exponential form. So now what I'd want to do is I'd want to come on back, and since I've got 8x, but I'm supposed to be solving for x, I'm going to come in and divide by 8. Those 8's will simplify out, and I'll be left with x is equal to e squared divided by 8. Now, a lot of people do not know what e squared is going to be, and so the fact is here we're going to have to use either a calculator or Desmos to figure it out, to approximate. Because again, remember I said e is an irrational number. Well, when you square an irrational number, you still get another irrational number. So let's take a look at how we could do this on the calculator. All right. So on the calculator, I have the e. If you notice, if you press second, and then the natural logarithm key, you can see above it, it says e raised to the x power. So that's what we're going to do. We're going to select that one. And then it needed to be squared and then divided by 8. There we go. So now I'm going to divide by 8. And this will give us our value for x, approximately. All right, so again, it's an irrational number. It's never going to stop. It's never going to repeat itself. But in this case, what I'd probably record is 0.924. All right, 0.924. So this is approximately 0.924. And that would be our answer. I've solved for x, approximately. All right, number 18, the last one. Let's take a look. I have the natural log of x minus the natural log of 9 is equal to 7. So I see that I've got a subtraction there, so that's let me know that I probably need to use one of my properties because I do not have just a single logarithm. And the property I would need to use here is my quotient property. Because it says if two logarithms with the same base are being subtracted, then all you have to do is divide the arguments. The first logarithm, the argument goes in the numerator. Second logarithm, the argument goes in the denominator. So let's go ahead and do that. We are going to go ahead and condense these logarithms so they're both natural logs. So I'm going to just go ahead and start here. We'll say natural log of x divided by 9. Because remember, when we're subtracting, we're using the quotient property. And it simply says take the first logarithm, that value will go, the argument will go in the numerator. Second logarithm, the value will go in the denominator. Now it's condensed, it's isolated, I don't have anything else to do, so this is where we'll come along and rewrite it in exponential form. So I have e to the 7th power, because it's my base, 7 was my exponent, and then in here, what we call the mantissa, is x over 9. Now, to finish solving for x, right now x is being divided by 9, so we're going to multiply by 9. So, for this problem, let's see what its solution is. We've got x equals 9 times e to the 7th power, or I can approximate it. So this first one here is what we would call our exact answer. That would be my exact answer. But normally we're going to approximate it. So I'm going to come back over here to Desmos. I'm going to take 9. Hang on. Yeah, 9 times e. And in Desmos, you just use the E key, like anything else, raised to the 7th power. Yep, 7th power. And so for this one, we get about 9,869.698. So 9,869. And then we have 0.698. Now, a couple of things that I didn't do on some of these problems, and just because I forgot, I wanted to move along, is we still need to check our solutions. Just because they're natural logarithms doesn't mean that our solutions are automatically going to work. So like here in this first one, in number 18, what I could do, let's come over to Desmos, I got my value there. Now, because I'm rounding, I may not get exactly 7. But let's see, what did I have? I had the natural log of x, so natural log of 9,869.698 was the first part of the equation, minus the natural log of 9. And so we know that because of rounding, I'm probably not going to get exactly 7. But notice what Desmos gives us, 6.9999999, and then some other non-9 digits. So this is essentially 7. So since it's so close to 7, even though it's under, sometimes it might be a little bit over, but because it's so close to 7, we'll say we're correct. All right. So again, you can do the math with Desmos. You can also check with Desmos. So until Wednesday, have a great rest of your day and a great weekend, and I will see you all on Wednesday. So remember, there will be no tutorials on Monday A or Tuesday A because I will not be here. But I'll be open both lunches, A and B, starting Wednesday. Until then, have a great rest of your day and a great weekend.